Before we begin, I'd love to know where in the world you're watching or listening from tonight. A quiet bedroom with the lights dimmed, a late-night train ride somewhere between cities, a comfortable sofa with a warm drink close by. Wherever you are, hopefully you're settled in, relaxed, and ready to drift gently into tonight's idea. If these calm explorations of science are something you enjoy, please consider liking the video and subscribing to the channel. It really helps this sleepy little corner of the universe continue drifting along. And to those already subscribed, thank you. Truly, your support means more than words can easily express. Now, tonight's topic might seem a little unusual, because the universe, when looked at carefully, is not the loud and chaotic place many people imagine. In fact, when astronomers measure the vast distances between stars and galaxies, something rather curious appears. The universe is incredibly quiet. Not quiet in the sense that nothing happens, far from it. Stars explode, galaxies collide, black holes swallow entire suns. But across the enormous emptiness of space, most of these dramatic events fade into something almost peaceful. From our tiny vantage point on Earth, the cosmos often appears calm, still, and strangely silent. It is as if the universe itself prefers quiet. Which raises a rather interesting question. Why is the universe so quiet? On a clear night, the sky can feel almost impossibly calm. Stars hang quietly overhead, scattered across darkness like distant lanterns. They do not roar, flicker wildly, or rush across the sky. Instead, they appear steady, distant, and strangely patient. Even the brightest of them simply glows. For most of human history, this quiet view of the cosmos was all anyone had. And it gave rise to some very different ideas about what the universe was actually like. In ancient astronomy, the sky was not imagined as empty at all. It was often thought of as a carefully arranged structure, almost like a layered machine. The Greek philosopher Aristotle proposed that the heavens were composed of perfect celestial spheres, each one carrying planets and stars around the Earth in smooth circular motions. In this view, the cosmos was orderly, elegant, and packed with structure. The sky looked calm, yes, but it was assumed to be full. Medieval scholars inherited these ideas and expanded them. The heavens were believed to contain nested spheres made from a mysterious perfect substance called the quintessence. The moon moved within one sphere, the sun within another, and the distant stars were fixed to a final outer shell that slowly rotated around everything else. It was a universe that felt complete, almost architectural, but it was also very small. Even the most ambitious medieval thinkers imagined the cosmos as a structure not vastly larger than the solar system. The stars were distant, certainly, but not unimaginably so. There was no sense of the staggering scale that modern astronomy would eventually reveal. That revelation began slowly. The invention of the telescope in the early 1700s allowed astronomers to see the heavens in far greater detail. Suddenly the sky was not just a scattering of points of light. It contained clouds, clusters, and faint smudges of brightness that seemed to drift among the stars. At first, no one quite knew what these objects were. Some thought they were nearby gas clouds, others suspected they were distant star systems. The uncertainty lingered for decades, quietly building toward one of the most important debates in the history of astronomy. In the early 20th century, two astronomers found themselves at the centre of that debate, Harlow Shapley and Heber Curtis. Their disagreement, which became known as the Great Debate of 1920, focused on a deceptively simple question. How big is the universe? Shapley argued that the Milky Way galaxy was enormous, and that the mysterious spiral nebulae seen through telescopes were simply smaller clouds of gas within it. Curtis believed something far more dramatic. He suggested that those spiral shapes might be entire galaxies in their own right, vast collections of stars lying far beyond the boundaries of the Milky Way. At the time, both possibilities seemed plausible. The debate was not settled immediately. But within a few years, a quiet revolution arrived. An astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, began studying one of those spiral nebulae using the 100-inch Hooker telescope, which was then the most powerful telescope in the world. Hubble focused on a faint object known as the Andromeda Nebula. What he discovered changed everything. Within the hazy spiral shape, Hubble identified individual stars whose brightness varied in a predictable pattern. These stars belonged to a class known as Cepheid variables, whose true luminosity had been carefully studied by the astronomer Henrietta Swan Leavitt. Leavitt had discovered a remarkable relationship between the brightness of these stars and the time they took to brighten and dim. By measuring that cycle, astronomers could determine how intrinsically bright a Cepheid star actually was. Comparing that intrinsic brightness to how faint it appeared from Earth allowed its distance to be calculated. When Hubble performed that calculation for the stars in the Andromeda Nebula, the result was astonishing. The object was far beyond the boundaries of the Milky Way. It was not a nebula at all. It was an entirely separate galaxy. Suddenly the universe expanded from a single galaxy into a vast collection of them. Each galaxy contained billions of stars, and each one floated through immense stretches of space that separated it from its neighbours. The cosmos had just become incomprehensibly larger, and with that new scale came a new realization. Most of the universe was empty. This was not a small emptiness either. The distances between galaxies could stretch across millions of light years. Even within galaxies, stars were separated by enormous gulfs of space. Our own Sun, for example, lies about 4 light years from the nearest star system, Alpha Centauri. That means light itself, travelling at the fastest speed known in nature, takes more than 4 years just to cross the gap. Between those stars lies almost nothing, just a faint scattering of atoms drifting through the interstellar medium. This realization led to a profound shift in how astronomers thought about the cosmos. The universe was not a tightly packed machine of celestial spheres. It was something far stranger, a vast structure made mostly of emptiness. Cosmologist Edward Harrison later reflected on this idea while studying the large-scale structure of the universe. Harrison pointed out that the apparent quietness of the cosmos does not mean that little is happening. Instead, it reflects the geometry of space itself. Matter gathers into galaxies and clusters under the influence of gravity, while the space between them stretches across enormous distances. The result is a universe that appears calm when viewed from afar. But that calmness is deceptive. Inside galaxies, stars are constantly forming within dense clouds of gas. Elsewhere, massive stars explode in supernovae powerful enough to briefly outshine entire galaxies. Black holes swallow matter, neutron stars collide, and streams of radiation burst across intergalactic space. Yet across the scale of the universe, these events are separated by such vast distances that the cosmos still feels quiet. This idea fascinated the theoretical physicist John Archibald Wheeler. Wheeler spent much of his career thinking about the deep structure of reality, from black holes to quantum mechanics. One question he often returned to was deceptively simple. Why does a universe capable of such extraordinary energy appear so calm when observed from afar? Why does the night sky feel peaceful rather than chaotic? Part of the answer lies in the sheer scale of the cosmos. When events are separated by millions or billions of light years, they rarely overlap from our perspective. Each one becomes an isolated flicker in the distance rather than part of a constant cosmic storm. But another part of the answer lies in the nature of space itself. Because the quietness of the universe is not only about distance, it is also about silence. The vast emptiness between stars and galaxies does something remarkable. It prevents most forms of vibration from travelling across the cosmos. The explosions of distant stars do not roar through space the way thunder rolls through Earth's atmosphere. Instead, they unfold in near-perfect silence. which raises a curious thought. Perhaps the universe is not truly quiet because little is happening. Perhaps it simply lacks the conditions needed for us to hear it. And understanding that idea begins with a simple question: what exactly is sound? To understand why the universe feels so quiet, it helps to begin with something familiar: sound. On Earth, sound is everywhere. The rustle of leaves, the hum of distant traffic, the gentle tapping of rain against a window. Even in places that feel peaceful, the air is usually filled with tiny vibrations moving quietly from one place to another. But sound is not simply a thing that exists on its own. It is a process. At its most basic level, sound is a mechanical vibration traveling through matter. When something moves or strikes another object, it causes nearby particles to jostle back and forth. These movements pass from particle to particle in a chain reaction, spreading outward like ripples across water. That travelling ripple is what the human ear detects as sound. Air carries these vibrations extremely well. When someone speaks, the vocal cords push air molecules forward and backward in rapid pulses. Those pulses move outward through the atmosphere, eventually reaching another person's ears where they're converted into electrical signals by the auditory system. Water can carry sound too. In fact, sound moves even faster through water than it does through air, which is why whales can communicate across enormous distances beneath the ocean surface. Solid materials can transmit vibrations as well. If someone presses an ear against a railway track, the rumble of an approaching train can sometimes be heard long before it becomes audible in open air. In all of these cases, something important is present: matter. Sound needs particles. It requires atoms or molecules close enough together that they can bump into one another, passing energy along step by step. Without those particles, the vibration simply has nothing to push against. This idea may seem obvious today, but there was a time when scientists were not entirely certain how sound behaved in empty space. In the 17th century, natural philosophers began experimenting with ways to create artificial vacuums, attempting to remove air from sealed containers. One of the earliest pioneers in this area was the German scientist Otto von Guericke. Von Guericke is remembered for a dramatic demonstration involving two large metal hemispheres that had been fitted together and evacuated of air. Teams of horses attempted to pull the hemispheres apart but failed, revealing just how powerful atmospheric pressure could be. But von Guericke also explored a quieter question: what happens to sound when air is removed? His experiments suggested that sound weakened dramatically in a vacuum. Later scientists refined these tests, including the English chemist and physicist Robert Boyle. Boyle placed a ringing bell inside a glass chamber and gradually pumped out the air. As the air disappeared, the bell continued to vibrate, but its sound faded until it became nearly impossible to hear. The bell was still ringing, but the sound had nowhere to go. These early vacuum experiments helped establish one of the key principles of acoustics. Sound requires a medium through which vibrations can travel. Remove the medium, and the vibrations remain trapped at their source. Later scientists expanded this understanding by studying how vibrations move through different materials. In the 18th century, the German physicist Ernst Chladni conducted elegant experiments with vibrating plates. By sprinkling fine sand across metal plates and then drawing a violin bow along the edges, Chladni caused the plates to vibrate in specific patterns. The sand gathered into intricate geometric shapes that revealed how sound waves moved across the surface. These patterns, now known as Chladni figures, provided one of the earliest visual demonstrations of wave behavior in solid materials. A century later, Hermann von Helmholtz deepened the scientific understanding of acoustics by studying how sound waves interact with the human ear and with physical objects. Helmholtz showed that sound could be analysed mathematically as oscillating pressure waves moving through matter. Put simply, sound is motion passed from particle to particle, which brings us to space. The environment between the stars is almost unimaginably empty. On Earth, Even the cleanest air contains billions upon billions of molecules in every small volume. In contrast, the space between stars contains only a few atoms per cubic centimetre, sometimes fewer. This thin scattering of gas is known as the interstellar medium, a term widely studied by the astrophysicist Lyman Spitzer during the 20th century. Spitzer helped reveal that although space appears empty, it does contain faint traces of hydrogen gas dust grains and ionized particles drifting through the galaxy. But the key word here is faint. The particles are so widely separated that they rarely interact with one another. Imagine standing in a room where the nearest person is several kilometers away. Passing a vibration along a chain of people would become nearly impossible. That is essentially the situation in interstellar space. Even if a star explodes in a spectacular supernova, sending shock waves racing outward at tremendous speeds, those waves quickly thin out as they spread into the near vacuum surrounding them. The particles are simply too far apart to transmit a continuous sound wave across large distances. The explosion would still release enormous energy, but it would unfold in silence. This silence does not mean that nothing moves through space. Quite the opposite. Space is filled with other forms of energy that travel in very different ways. Light, for example, can cross the vacuum of space without difficulty, because electromagnetic radiation does not require a material medium. It moves through the fabric of space itself, carrying energy and information across immense distances. There are also more exotic forms of motion present in cosmic environments, in regions where gas becomes ionized, meaning the atoms lose some of their electrons, the particles become electrically charged. Charged particles respond strongly to magnetic fields, and their behavior can produce complex patterns of motion, known as plasma waves. These phenomena were explored in detail by the Swedish physicist Hannes Alfvén, who developed the field of magnetohydrodynamics. This branch of physics studies how electrically conducting fluids, such as plasma, interact with magnetic fields. Alfvén showed that in certain cosmic environments, waves can travel through ionized gas along magnetic field lines, transferring energy across space in ways that resemble sound, but are governed by electromagnetic forces. These plasma waves are fascinating, but they are not sound in the everyday sense. They occur under very specific conditions and do not propagate through the vast majority of interstellar space. For ordinary sound, the requirement remains simple. Particles must be close enough together to pass vibrations along. In space, they usually are not. This is why astronauts floating outside a spacecraft cannot hear an explosion nearby unless the vibration travels through the structure of the spacecraft itself. The surrounding vacuum provides no pathway for the sound to reach them. The universe, in that sense, is profoundly quiet. Not because events do not occur, but because the environment between those events prevents vibrations from travelling freely. Yet the silence of space is only part of the story. Even more striking than the vacuum itself are the enormous distances that separate the stars. Distances so vast that entire solar systems drift through the galaxy without ever coming close to one another. And once those scales are considered, the quietness of the universe begins to feel less surprising. It begins to feel inevitable. Once the silence of space is understood, another feature of the universe begins to stand out even more clearly. Distance. Not the ordinary kind experienced on Earth, where cities lie a few hundred kilometers apart and oceans span a few thousand. The distances between stars are of an entirely different scale, so vast that human intuition struggles to picture them accurately. The nearest star system to Earth, known as Alpha Centauri, lies a little more than 4 light-years away. That means light, which moves faster than anything else known in nature, takes more than 4 years to travel from that star to our planet. 4 years, and that is the closest one. Within the Milky Way galaxy there are hundreds of billions of stars, yet they are separated by enormous gulfs of space. Our solar system occupies a tiny gravitational bubble around the Sun, and even that bubble stretches for trillions of kilometers before the Sun's influence begins to fade. Beyond that boundary lies a dark region of interstellar space that continues for years of light travel before another star system appears. If the Sun was shrunk to the size of a small coin resting on a table, the nearest star would still be thousands of kilometers away. It is no exaggeration to say that stars drift through a galaxy that is mostly empty. For centuries, however, astronomers had no reliable way to measure these staggering distances. The stars looked like tiny points of light in the sky, and without a sense of depth, it was nearly impossible to know how far away they truly were. The breakthrough arrived during the early 19th century through the careful work of the German astronomer Friedrich Bessel. Bessel used a technique known as stellar parallax, which relies on the motion of Earth around the Sun. As Earth travels along its orbit over the course of a year, nearby stars appear to shift slightly against the background of more distant stars. It is a very small shift, so small that detecting it required years of careful observation and extremely precise instruments. In 1838, Bessel successfully measured the parallax of a star known as 61 Cygni. From that tiny shift in position, he calculated the star's distance from Earth. For the first time in history, humanity had a reliable measurement of the distance to another star. The result confirmed what some astronomers had long suspected: the stars were unimaginably far away. As the 19th and early 20th centuries progressed, astronomers began cataloguing stars in greater detail. Observatories around the world mapped their brightness, colours, and spectral signatures. These observations slowly revealed that stars were not random points scattered through space, but part of a vast population distributed across the Milky Way. One of the astronomers who contributed significantly to this work was Annie Jump Cannon at the Harvard College Observatory. Cannon developed a classification system that organized stars according to their spectral characteristics, effectively sorting them by temperature. Her system, still used today, revealed that stars come in distinct categories ranging from extremely hot blue stars to cooler red ones. This classification helped astronomers understand how stars differ from one another and how they are distributed throughout the galaxy. Another key figure in this growing understanding was Cecilia Payne-Gaposchkin. In the 1920s, Payne-Gaposchkin analysed stellar spectra and made a remarkable discovery. She demonstrated that stars are composed primarily of hydrogen and helium, overturning earlier assumptions that their composition resembled Earth. Her work revealed that stars share a common chemical foundation, suggesting that the galaxy itself formed from vast clouds of gas that eventually condensed into individual stellar systems. Each of those systems then evolved largely on its own. This idea was later explored in depth by the astrophysicist Subrahmanyan Chandrasekhar, who studied the physical limits governing stellar structure. Chandrasekhar showed that stars are held in balance by a competition between gravity pulling inward and pressure from nuclear fusion pushing outward. This balance allows stars to remain stable for extremely long periods. Many stars live for billions of years without dramatic changes in brightness or motion. They burn quietly, slowly converting hydrogen into helium within their cores. In other words, once stars form, they tend to settle into long, stable lives. This stability contributes to the calm appearance of the galaxy. Even though stars contain immense energy, most of that energy is released gradually over millions or billions of years. There are exceptions, of course. Some stars eventually explode in supernova events, releasing enormous bursts of energy. But these explosions are rare when viewed across the entire galaxy. Most stars simply glow steadily in the darkness. Another important insight into stellar spacing came from careful observations of star distributions across the sky. Among the many observers who contributed to this effort was the Indian astronomer Radha Gobinda Chandra. Working largely with modest equipment, Chandra spent years observing variable stars and tracking their brightness over time. His work, along with that of other dedicated observers around the world, helped astronomers build a clearer picture of how stars populate the Milky Way. What emerged from these observations was the concept of stellar neighbourhoods. Stars are not evenly scattered like grains of sand. Instead, they often form loose groups or clusters that share similar origins. Some clusters contain hundreds or thousands of stars bound together by gravity. But even within these groups, the distances between individual stars remain immense. Gravity holds the cluster together, yet the stars themselves rarely come close enough to interact directly. In fact, direct collisions between stars are extraordinarily rare events. Consider our own Sun as an example. As it orbits the centre of the Milky Way, it travels through the galaxy at a speed of roughly 200 kilometers per second. Over millions of years, it passes through different regions of space and occasionally moves near other stars. Yet the distances involved are so great that these encounters almost never lead to collisions. Stars simply glide past one another, like ships drifting across a vast and nearly empty ocean. This spacing has profound consequences for the appearance of the universe. Because stars are so widely separated, their light reaches us individually rather than blending into a constant glow. Each star becomes a single point of brightness against the night sky, surrounded by enormous regions of darkness. If stars were packed more closely together, the sky would look very different. The darkness between them would shrink, and the heavens might appear filled with continuous light. Instead, the galaxy resembles a sparse archipelago of stars floating in a sea of emptiness. This separation also contributes to the quietness of the cosmos. Events occurring around one star system rarely influence another. A supernova explosion in a distant region of the galaxy may unleash staggering amounts of energy, but by the time its radiation spreads across the vast gulf separating stars, it becomes faint and diffuse. The universe is active, but it is active at a distance, and that distance softens everything. The result is a galaxy that appears calm, even while enormous physical processes unfold within it. Yet the Milky Way itself is only one example. When astronomers step back and look at galaxies as a whole, they discover something even more surprising. Entire galaxies are also separated by immense regions of empty space. When the immense distances between stars become clear, another realization begins to take shape. The galaxy itself is also mostly empty. From Earth, the Milky Way appears as a faint river of light stretching across the night sky. Under truly dark conditions, far from city lights, it can look almost like a misty cloud arching overhead. For many centuries, it was simply called the Milky Way because of this soft milky glow. But that glow hides an enormous structure. The Milky Way is a spiral galaxy, a vast rotating system of stars, gas, dust, and dark matter bound together by gravity. Its visible portion stretches roughly 100,000 light-years from one side to the other, forming a broad, flattened disk that slowly rotates through space. And within that disk are hundreds of billions of stars. That number sounds crowded, yet the reality is quite the opposite. Those stars are scattered across such enormous distances that even the dense regions of the galaxy contain far more empty space than matter. Most stars drift through regions where their nearest stellar neighbours remain several light-years away. The galaxy is immense, but the emptiness inside it is even greater. Spiral galaxies like the Milky Way share a common structure that astronomers have studied for decades. At the centre lies a dense region known as the galactic bulge, where stars gather more closely together around a supermassive black hole. Surrounding this bulge is the galactic disk, a wide rotating plane that contains most of the galaxy's stars. Threaded through that disk are the famous spiral arms. These arms are not rigid structures like the blades of a fan. Instead, they are regions where gas and stars become slightly more concentrated as they orbit the galactic centre. Over time, waves of density move through the disk, compressing clouds of gas and triggering the birth of new stars. The result is a galaxy with glowing spiral patterns that appear almost like cosmic whirlpools. Beyond the disk lies another component known as the galactic halo. This region extends far above and below the galaxy's main plane and contains scattered stars, ancient globular clusters and a mysterious form of matter that cannot be seen directly. Dark matter. The existence of dark matter became clear during the 1970s through the work of the American astronomer Vera Rubin. Rubin carefully measured how stars move within spiral galaxies by studying their rotation curves, which describe how orbital speed changes with distance from the galactic center. According to classical gravitational physics, stars farther from the center of a galaxy should orbit more slowly. The visible mass of the galaxy should not provide enough gravity to keep them moving quickly. But Rubin found something unexpected. Stars at the outer edges of galaxies were orbiting just as fast as those closer to the center. This observation suggested that galaxies contain far more mass than what can be seen in stars and gas alone. The extra gravity had to be coming from something invisible, a substance that does not emit light but still exerts gravitational influence. This invisible component became known as dark matter. Rubin's observations transformed the way astronomers think about galaxies. It now appears that most of a galaxy's mass exists in an enormous halo of dark matter surrounding the visible disk, and that halo extends far beyond the regions filled with stars. The idea that galaxies contain hidden mass had actually been proposed decades earlier by the Swiss astronomer Fritz Zwicky. In the 1930s, Zwicky studied clusters of galaxies and noticed that the galaxies within those clusters were moving far too quickly to be held together by visible matter alone. He concluded that some form of unseen matter must be present, adding gravitational strength to the system. Zwicky referred to this mysterious substance as dark matter. At the time, the idea received little attention, but later observations, including Rubin's rotation curve measurements, strongly supported the concept. Today, dark matter is considered one of the central components of cosmic structure. It shapes the formation of galaxies, influences their motion, and helps explain why these vast systems remain stable over billions of years. Even so, the presence of dark matter does not make galaxies crowded. Far from it. The stars themselves occupy only a tiny fraction of the total volume within a galaxy. Astronomers studying galactic dynamics have long worked to understand how these stars are distributed and how they move collectively through space. One important contribution came from the American astronomer Sandra Faber, who helped develop what is known as the Faber-Jackson relation. This relationship links the brightness of certain galaxies with the velocities of the stars moving inside them. By studying these motions, astronomers can estimate the mass and internal structure of galaxies, revealing how gravity organizes their enormous populations of stars. The results consistently point to the same conclusion. Galaxies are vast systems, but they are remarkably sparse. Most of their volume contains little more than drifting gas and faint dust particles. The stars themselves remain widely spaced, orbiting the galactic center like distant islands in a cosmic ocean. Understanding how galaxies form also reveals why this emptiness persists. Modern cosmology suggests that galaxies did not appear all at once. Instead, they grew gradually through a process known as hierarchical merging. In this scenario, small clumps of matter formed first in the early universe, eventually merging together under gravity to build larger and larger structures. Cosmologists such as Simon White and Carlos Frenk helped develop detailed computer simulations showing how this process might unfold over billions of years. Their models demonstrated that dark matter plays a crucial role in guiding galaxy formation, providing the gravitational framework within which gas can gather and form stars. As galaxies assemble through mergers and accretion, their stars spread out across enormous regions of space. The result is a structure that is massive but extremely diffuse. Even a galaxy containing hundreds of billions of stars still leaves most of its volume unoccupied. The distances between stars remain so large that direct collisions are extraordinarily rare. Entire solar systems can orbit the galaxy for billions of years without ever encountering another. This vast spacing also explains why galaxies appear calm when viewed from afar. Within any given galaxy, dramatic events do occur. Massive stars collapse into neutron stars. Supernova explosions release staggering bursts of energy. Black holes consume surrounding matter and unleash powerful jets of radiation. Yet these events are scattered across distances measured in thousands or even tens of thousands of light years. Each one becomes an isolated flicker of activity rather than part of a continuous cosmic storm. The galaxy, taken as a whole, appears peaceful. It is a quiet archipelago of stars drifting through a sea of darkness. And the Milky Way is only one example among many. Across the observable universe there are hundreds of billions of galaxies, each one separated from its neighbours by immense stretches of space. When astronomers map these galaxies across the sky, they discover that even galaxies themselves are not evenly distributed. They gather into clusters and filaments, leaving enormous regions where very little matter exists at all. These immense structures form a pattern that stretches across the entire universe, a pattern sometimes described as the cosmic web. An understanding that web reveals an even deeper layer of cosmic emptiness. When astronomers first began mapping galaxies across the sky, they expected something relatively simple. Perhaps galaxies would be scattered randomly, like grains of sand tossed across a surface. Or perhaps they would spread out smoothly in all directions, forming a gentle cosmic fog of stars and galaxies drifting through space. But the universe had something far more interesting in mind. As larger and more detailed surveys of the sky began to appear during the late 20th century, astronomers noticed that galaxies were not distributed evenly at all. Instead, they gathered into clusters, chains, and enormous curved structures stretching across the universe. Between these structures lay enormous regions containing almost nothing. This grand pattern is now known as the cosmic web, and once seen, it becomes impossible to forget. Imagine looking at the universe from far beyond the boundaries of the Milky Way. Instead of a smooth cloud of galaxies, you would see something resembling a vast three-dimensional network. Long filaments of galaxies stretch across space, connecting dense clusters like strands of glowing thread. These filaments weave together into an intricate lattice that extends across the observable universe. In between those strands lie enormous empty regions called cosmic voids. The structure resembles a sponge, or perhaps the delicate foam of bubbles on the surface of water, except the bubbles are hundreds of millions of light years across. This extraordinary architecture did not emerge as a surprise to everyone. Decades before astronomers had the observational tools to map galaxies across such enormous distances, a Soviet physicist named Yakov Zeldovich had already begun to suspect that the universe might organize itself into filamentary structures. Zeldovich studied how gravity influences the growth of matter in the expanding universe. His work focused on what happens when tiny variations in density begin to grow under the influence of gravitational attraction. Even in the early universe, matter was not perfectly uniform. Some regions were slightly denser than others. Those slightly denser regions exerted a little more gravitational pull, drawing in surrounding matter over time. This process is known as gravitational instability. Over millions and then billions of years, these small irregularities gradually grew larger. Zeldovich predicted that as matter collapsed under gravity, it would not gather into perfectly spherical clusters. Instead, it would collapse first into sheets, then into filaments, and finally into dense nodes where filaments intersect. These nodes would eventually become clusters of galaxies. For many years, this idea remained largely theoretical. Observing the large-scale structure of the universe required mapping galaxies across vast regions of space, something that earlier telescopes and surveys could not easily accomplish. That situation changed dramatically toward the end of the 20th century. Large collaborative projects began to measure the positions and distances of hundreds of thousands, and eventually millions, of galaxies. One of the most influential of these efforts was the Sloan Digital Sky Survey. an ambitious astronomical project that began mapping the universe in the early 2000s. Using a dedicated telescope located at Apache Point Observatory in New Mexico, the Sloan Digital Sky Survey recorded the positions and spectral properties of enormous numbers of galaxies. By measuring how their light was shifted toward the red end of the spectrum through a process known as cosmological redshift, astronomers could determine how far away those galaxies were. With these measurements, they began constructing three-dimensional maps of the universe. What those maps revealed was breathtaking. Galaxies were not scattered randomly. They were arranged along immense filaments stretching across hundreds of millions of light years. These filaments intersected at dense nodes where clusters of galaxies gathered under powerful gravitational forces. Between them were vast empty spaces. Later observational efforts such as the Dark Energy Survey expanded these maps even further, capturing images of hundreds of millions of galaxies across large portions of the sky. These surveys allowed astronomers to trace the cosmic web in ever greater detail, confirming the large-scale structure predicted by Zeldovich decades earlier. The universe, it seemed, truly was woven like a vast cosmic net. Within this net, some of the most intriguing regions are the cosmic voids. These voids are immense volumes of space containing very few galaxies. In some cases, they stretch across hundreds of millions of light years, while holding only a handful of scattered galaxies. Compared with the dense filaments of the cosmic web, these regions are almost completely empty. Astronomers have studied these voids carefully in order to understand how matter is distributed throughout the universe. One of the researchers who helped clarify our place within this vast structure is Brent Tully, an astronomer known for his work on large-scale galaxy motions. Tully and his collaborators identified a massive region of interconnected galaxy clusters known as the Laniakea supercluster. The name Laniakea comes from a Hawaiian phrase meaning immense heaven, a fitting description for such a colossal structure. The Milky Way galaxy resides within this enormous gravitational basin, which contains roughly 100,000 galaxies moving slowly toward a common centre of gravitational attraction. Yet even a structure as large as Laniakea occupies only a small portion of the surrounding cosmic landscape. Beyond its boundaries lie enormous voids where galaxies become increasingly scarce. Some of these voids are so large that light itself takes hundreds of millions of years to cross them. Inside them, matter is spread so thinly that entire regions of space contain almost no galaxies at all. The universe, on its largest scales, resembles a delicate lacework of matter suspended across enormous distances. Understanding why this structure forms requires returning to the role of gravity. Gravity is a remarkable force because it acts over unlimited distances. Even small concentrations of matter can gradually pull surrounding material toward them over time. When the universe was young, tiny fluctuations in density began to grow through this gravitational attraction. Denser regions slowly gathered more material, while less dense regions gradually lost matter to their surroundings. Over billions of years, this process amplified itself. Matter flowed toward the growing filaments and clusters, leaving behind vast underdense regions that became cosmic voids. The more matter gathered into filaments, the emptier the surrounding regions became. In this way, the architecture of the universe naturally created enormous volumes of quiet emptiness. The cosmic web is therefore not just a visual curiosity, it is a direct consequence of the laws of gravity acting over immense spans of time and space. Clusters of galaxies form the glowing intersections of this web. Filaments stretch outward like cosmic highways connecting these clusters, and between them lie vast regions where almost nothing exists at all. These voids represent some of the most peaceful regions in the universe. Few galaxies reside there. Few energetic events occur. The darkness inside them is profound, interrupted only by faint light from distant structures far beyond their boundaries. It is within this enormous architecture that the quietness of the cosmos becomes most obvious. The universe is not merely empty in small patches, Its emptiness is built into the very geometry of cosmic structure. Matter gathers along filaments and nodes, leaving immense regions of silence between them. The largest structures in existence therefore create the largest spaces where almost nothing happens. A cosmic stillness written into the architecture of the universe itself. Yet this raises an even deeper question. If the cosmic web emerged from tiny fluctuations in matter, where did those fluctuations come from in the first place? To answer that, the story must travel much farther back in time, back to the earliest moments of the universe itself. The quiet universe seen today did not always exist in this calm state. In fact, if someone could travel far enough back in time, the cosmos would appear almost unimaginably different. The vast emptiness between galaxies, the gentle glow of distant stars, and the slow drifting of cosmic structures would give way to something far more energetic. The early universe was not quiet at all. It was dense, hot, and filled with radiation. Shortly after the beginning of cosmic expansion, the entire observable universe existed in a state where matter and energy were compressed together at extraordinary temperatures. Instead of galaxies and stars, space contained a turbulent mixture of elementary particles, radiation, and plasma. Photons, electrons, and protons interacted constantly, colliding and scattering in every direction. The universe at that time behaved less like a calm cosmic landscape and more like a blazing ocean of energy. Understanding how scientists came to this conclusion begins with a remarkable idea proposed during the early 20th century by the Belgian physicist and priest, Georges Lemaitre. Lemaitre suggested that the universe was not static or eternal in its present form. Instead, he proposed that it had expanded from a much smaller and denser state in the distant past. In 1927, Lemaitre described a universe that was gradually stretching over time, with galaxies moving away from one another as space itself expanded. He referred to the original state of the universe as the primeval atom, imagining all matter once compressed into a single, extremely dense beginning. This idea eventually became known as the Big Bang theory. At first, the concept was controversial. Many scientists preferred a static universe that had always existed. Even Albert Einstein initially resisted the notion of cosmic expansion, although he later acknowledged that the mathematical framework of general relativity allowed for such a possibility. Evidence for an expanding universe grew steadily as observations improved. Astronomers discovered that distant galaxies appear to move away from Earth, and the farther a galaxy lies, the faster it appears to recede. This pattern revealed that the fabric of space itself was stretching. If the universe is expanding today, then logically it must have been smaller in the past. Continue tracing that expansion backward far enough, and the universe reaches an earlier epoch when matter and radiation were compressed together into a hot, dense state. In that environment, energy filled every region of space. Particles collided constantly. Radiation scattered through the dense plasma. The universe behaved like a glowing cosmic furnace. This early period left behind a remarkable relic that astronomers would discover many billions of years later. In the 1960s, two radio astronomers named Arno Penzias and Robert Wilson were working with a sensitive microwave antenna at Bell Laboratories in New Jersey. They were studying faint radio signals from the sky when they encountered a persistent background noise that seemed to come from every direction. At first, they suspected a technical problem. They carefully checked the instrument, cleaned the antenna, and even removed nesting pigeons that had taken up residence inside the equipment. Yet the mysterious signal remained. Eventually they realized that the noise was not a malfunction at all. It was coming from the universe itself. What Penzias and Wilson had detected was the cosmic microwave background radiation, the faint afterglow of the early universe. This radiation originated roughly 380,000 years after the beginning of cosmic expansion, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, photons constantly scattered off free electrons in the dense plasma, preventing light from travelling freely. Once atoms formed, the universe became transparent to radiation, allowing photons to stream through space for the first time. Those ancient photons are still travelling today. Over billions of years, cosmic expansion stretched their wavelengths into the microwave region of the electromagnetic spectrum. What remains is an extremely faint radiation field that fills all of space. It is the oldest light that can be observed. But this ancient glow also contains subtle patterns. When astronomers studied the cosmic microwave background in greater detail, using satellites such as the Cosmic Background Explorer, and later the Wilkinson Microwave Anisotropy Probe and the Planck Observatory, they discovered tiny variations in temperature across the sky. These fluctuations were incredibly small, yet they carried profound meaning. They revealed that the early universe was not perfectly uniform. Some regions were slightly denser than others. These small differences in density served as the seeds from which galaxies and galaxy clusters eventually formed. Gravity slowly amplified these fluctuations, pulling matter into growing structures across billions of years. The early universe was therefore filled with ripples, not only in matter, but in sound. During the first several 100,000 years after cosmic expansion began, the universe consisted of a hot plasma of electrons, protons, and photons. In this environment, pressure from radiation pushed outward, while gravity pulled matter inward. This balance created oscillations in the plasma. Regions of slightly higher density would collapse under gravity, compressing the plasma. Radiation pressure would then push outward again, causing the region to expand. The result was a series of rhythmic waves moving through the early universe. These waves are known as baryon acoustic oscillations. Although they occurred in an extremely hot plasma rather than in ordinary air, the physical principle was remarkably similar to sound waves. Pressure and gravity created oscillations that propagated through the dense medium of the young universe. Cosmologists such as Daniel Eisenstein have studied these oscillations carefully because they left a measurable imprint on the distribution of galaxies across cosmic space. The spacing between large-scale structures today still reflects the pattern created by those ancient waves. In other words, the large-scale structure of the universe still carries the memory of sound waves that travelled through the primordial plasma. Another fascinating interaction between radiation and matter was described by the astrophysicist Rashid Sunyaev. Working with Yakov Zeldovich, Sunyaev studied how the cosmic microwave background radiation interacts with clusters of galaxies. When ancient microwave photons pass through the extremely hot gas inside a galaxy cluster, they can gain energy by scattering off energetic electrons. This process slightly alters the energy distribution of the background radiation. The effect is now known as the Sunyaev-Zeldovich effect. Astronomers use this phenomenon as a powerful observational tool to study galaxy clusters and trace large-scale structures across the universe. It provides yet another reminder that the early universe was a place of intense interactions between radiation and matter, a place filled with motion, filled with energy, filled with sound like oscillations moving through cosmic plasma. Over time, however, the universe expanded. As space stretched outward, matter became more widely separated. The density of particles gradually decreased, and the intense interactions that once filled every region of space began to fade. The cosmic furnace slowly cooled. The plasma cleared, radiation thinned, and the universe began its long transition from a noisy, energetic beginning toward the quiet, spacious cosmos seen today. A transformation shaped by the expansion of space itself. As the early universe cooled and matter gradually gathered into the first stars and galaxies, another process continued quietly in the background. Space itself was expanding. This idea may sound abstract, at first, because it does not behave like an ordinary explosion. When something explodes on Earth, fragments are thrown outward through space. But the expansion of the universe is different. It is not galaxies moving through empty space away from a single central point. Instead, the space between galaxies is stretching. Every large region of the universe slowly grows larger over time, carrying galaxies farther apart from one another. The galaxies themselves are not flying through a static cosmic landscape. Rather, the fabric of space between them is gradually expanding. This concept began to take shape through the work of several scientists during the early 20th century. One of the most important theoretical contributions came from the Russian physicist Alexander Friedmann. In 1922, Friedmann examined the equations of general relativity developed by Albert Einstein and discovered something remarkable. Einstein's theory did not require the universe to remain static. In fact, Friedmann showed that the equations naturally allowed for a universe that either expanded or contracted over time. His solutions described how the geometry of space-time could evolve depending on the amount of matter and energy present. At the time, this idea seemed radical. Most scientists still imagined the cosmos as a fixed and eternal structure. Even Einstein had initially introduced a mathematical adjustment to his equations, known as the cosmological constant, in order to maintain a static universe. But the universe itself soon provided evidence that Friedmann's expanding solutions were correct. In the late 1920s, the astronomer Edwin Hubble carefully measured the light from distant galaxies at the Mount Wilson Observatory. By studying their spectra, he noticed that many galaxies exhibited a shift toward longer wavelengths of light. This phenomenon is known as redshift. When light from an object stretches toward the red end of the spectrum, it indicates that the object is moving away from the observer. The same effect can be heard with sound when a passing siren changes pitch as it moves past, a phenomenon known as the Doppler effect. Hubble discovered that galaxies were not only moving away from Earth, but that the speed of their recession increased with distance. The farther a galaxy appeared, the faster it seemed to be moving away. This relationship became known as Hubble's law. In simple terms, it states that the recessional velocity of a galaxy is proportional to its distance from the observer. The more distant the galaxy, the greater the redshift observed in its light. The underlying principle can be expressed in a compact mathematical form often written in physics as velocity equals the Hubble constant multiplied by distance. Although the equation itself is concise, its implications are enormous. If galaxies appear to be moving away from one another in every direction, the most natural explanation is that space itself is expanding. Just as dots drawn on the surface of an inflating balloon move farther apart as the balloon expands, galaxies become more widely separated as the universe grows larger. This expansion occurs everywhere at once. No single point in space serves as the center. From the perspective of any galaxy, all distant galaxies appear to be moving away in the same general pattern. Each observer sees themselves surrounded by a universe that is gradually stretching outward. Over billions of years, this expansion has had profound consequences for the structure of the cosmos. Galaxies that once formed relatively close groups slowly drift farther apart. Clusters of galaxies become more isolated from one another. The distances between large cosmic structures continue to grow as space itself expands. The universe becomes more spacious with time, and with greater distance comes greater quiet. When galaxies lie millions of light years apart, interactions between them become increasingly rare. The gravitational influence of one galaxy on another weakens with distance, and collisions between galaxies occur only occasionally across cosmic timescales. Most galaxies simply travel along their paths through expanding space, drifting quietly through the darkness. For many decades, astronomers assumed that this expansion would gradually slow down. Gravity, after all, pulls matter together. The combined gravitational attraction of all the galaxies in the universe should act as a cosmic brake, gradually reducing the rate of expansion over time. That expectation seemed reasonable. But the universe had another surprise waiting. During the late 1990s, two independent teams of astronomers set out to measure the expansion history of the universe using distant stellar explosions known as Type 1a supernovae. These supernovae occur when certain white dwarf stars accumulate too much mass and explode with nearly uniform brightness. Because their intrinsic brightness is well understood, astronomers can use them as cosmic distance markers. By comparing how bright these supernovae appear from Earth with how far away they are, researchers can estimate the expansion rate of the universe at different points in cosmic history. The teams studying these supernovae were led by Saul Perlmutter, Brian Schmidt, and Adam Rees. Their observations revealed something astonishing. The expansion of the universe was not slowing down. It was speeding up. Galaxies were drifting apart faster and faster over time, as though some invisible influence were pushing space outward. This discovery introduced a new concept into cosmology: dark energy. The term dark energy was popularized by the cosmologist Michael Turner to describe the mysterious force or property of space responsible for accelerating cosmic expansion. Unlike ordinary matter or radiation, dark energy does not appear to clump together into structures. Instead, it seems to be spread uniformly throughout space itself. Its exact nature remains one of the greatest open questions in modern physics. Some theories suggest that dark energy may be related to the cosmological constant originally introduced by Einstein. Others propose that it arises from the energy of the quantum vacuum or from fields that permeate space-time. Whatever its origin, the effect is clear. The universe is expanding at an accelerating pace. This acceleration has an important consequence for the long-term structure of the cosmos. As galaxies move farther apart, their interactions become increasingly rare. Over immense periods of time, many galaxies will drift beyond the observable horizon of others, carried away by the expanding fabric of space. The cosmic landscape gradually becomes more isolated. Clusters of galaxies remain bound together by gravity, forming local islands of matter. But beyond those clusters, the universe grows emptier and quieter as the distances between structures increase. The expansion of space therefore acts as a kind of cosmic calming mechanism. In the early universe, matter was packed closely together, and interactions between particles were constant. Over billions of years, expansion stretched those dense conditions into a far more spacious environment. Galaxies formed, clusters assembled, and vast regions of emptiness appeared between them. As the universe continues to expand, these separations will only grow larger. The cosmos will become increasingly quiet. Yet even within this expanding universe, information still travels. Light continues to cross enormous distances, carrying signals from stars, galaxies, and distant cosmic events. Across the growing calm of the cosmos, the universe still communicates. It simply does so in a language very different from sound. Silence, in the ordinary human sense, usually means an absence of sound. But the universe is not truly silent. It simply communicates in a very different language. On Earth, sound travels through air as tiny compressions and rarefactions of molecules. These pressure waves move through matter by pushing neighbouring particles, creating the familiar vibrations that eventually reach human ears. Space, however, contains almost no particles. Without a dense medium of molecules, sound waves have nothing to push against. Vibrations cannot propagate through the vacuum between stars in the same way they travel through air or water, and yet the universe is constantly sending signals across those empty distances. Those signals arrive in the form of light. Light belongs to a broader category of phenomena known as electromagnetic radiation. Unlike sound, electromagnetic radiation does not require a material medium to travel. Instead, it moves through space as oscillations of electric and magnetic fields that sustain each other as they propagate forward. This remarkable property allows light to cross the vacuum of space without losing its ability to carry information. The scientific explanation for this behaviour emerged during the 19th century through the work of the Scottish physicist James Clerk Maxwell. Maxwell studied electricity and magnetism, two phenomena that had previously been investigated separately by scientists such as Michael Faraday and André-Marie Ampère. Through careful mathematical analysis, Maxwell discovered that electric and magnetic fields are deeply connected. A changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. These two fields can reinforce one another in a self-propagating pattern that travels through space. Maxwell realized that such oscillations would move at a specific speed determined by the electrical and magnetic properties of space itself. When he calculated that speed, the result matched the measured speed of light. From this insight came a profound conclusion. Light itself is an electromagnetic wave. This realization unified several branches of physics into a single framework now known as classical electromagnetism. It also revealed why light can travel across the vacuum of space even when sound cannot. Sound requires matter. Light requires only fields. Once Maxwell's theory became widely accepted, scientists began to understand that visible light represents only a small portion of a much broader electromagnetic spectrum. Different forms of radiation vary in wavelength and frequency, yet all obey the same underlying principles described by Maxwell's equations. Radio waves occupy the longest wavelengths, microwaves follow next, then infrared radiation. Visible light lies roughly in the middle of the spectrum, representing the narrow band that human eyes evolved to detect. Beyond visible light come ultraviolet radiation, X-rays, and finally gamma rays, which carry enormous energy in extremely short wavelengths. Each region of the spectrum reveals different aspects of the universe. Some cosmic phenomena emit primarily radio waves, while others shine most strongly in infrared or X-rays. By studying multiple wavelengths of electromagnetic radiation, astronomers can piece together a far richer picture of cosmic activity. The sky, when viewed across the full electromagnetic spectrum, becomes far more dynamic than the quiet darkness seen with human eyes alone. A key figure in the early development of radio astronomy was the American engineer and radio enthusiast Grote Reber. During the 1930s, Reber built the first dedicated radio telescope in his backyard in Wheaton, Illinois. Using a large metal dish designed to collect radio waves from the sky, he began systematically mapping radio emissions from the Milky Way. His observations reveal that the galaxy emits radio signals even in regions where visible light appears faint or absent. These early discoveries opened an entirely new window onto the universe. Over time, radio astronomy expanded dramatically, allowing scientists to detect pulsars, study interstellar gas clouds, and observe distant galaxies that would otherwise remain hidden. Today, radio observatories operate on a scale that Reber could scarcely have imagined. One of the most remarkable facilities is the Atacama Large Millimeter Array, located high in the Atacama Desert of northern Chile. This array consists of dozens of precisely synchronized radio antennas spread across the desert plateau. Together they function as a single enormous telescope capable of detecting extremely faint radio signals from distant cosmic structures. These observations reveal cold clouds of gas where stars are forming, swirling disks of material around young stars, and even the faint afterglow of radiation left over from the earliest moments of cosmic history. Another revolutionary observatory is the James Webb Space Telescope. Launched into deep space beyond the orbit of the Moon, the James Webb Space Telescope observes the universe primarily in infrared wavelengths. Infrared light is particularly useful for studying distant galaxies and star-forming regions because it can pass through clouds of dust that block visible light. By detecting faint infrared signals that have travelled across billions of years of cosmic expansion, the telescope allows astronomers to glimpse galaxies that formed when the universe was still very young. Even objects that appear dark to human eyes can glow brightly in infrared radiation. Across the electromagnetic spectrum, the universe is constantly broadcasting information, Stars emit light produced by nuclear fusion in their cores. Galaxies shine with the combined glow of billions of stars. Black holes generate powerful radiation as matter spirals inward through hot accretion disks. Supernova explosions release bursts of electromagnetic energy, visible across vast cosmic distances. All of these signals move through space as electromagnetic waves. Even though space itself contains almost no air, these waves travel effortlessly across the vacuum. Light leaving a distant galaxy can cross billions of light years before reaching a telescope on Earth. That light carries a record of the conditions present when it was first emitted. By analysing its colour, intensity, and spectral features, astronomers can determine the temperature, composition, motion, and distance of the objects that produced it. In this way, light becomes the primary messenger of the universe. Every star in the night sky is sending a steady stream of photons across space. Every distant galaxy is quietly broadcasting its presence through electromagnetic radiation. The signals are everywhere, but they do not arrive as sound. They arrive as light. This difference explains why the universe appears silent when imagined through human senses. Our ears evolved to detect pressure waves in air, not oscillating electric and magnetic fields travelling through the vacuum of space. The cosmos may not roar or rumble in the traditional sense, yet it is far from inactive. Instead, it communicates continuously, through patterns of electromagnetic radiation that travel immense distances without the need for a medium. Through telescopes sensitive to different wavelengths, astronomers have learned to listen to this silent conversation of light. The universe speaks, just not in sound. And when those signals reveal the most energetic events in existence, they show that beneath the calm appearance of the cosmos lie extraordinary bursts of activity unfolding across unimaginable distances. The universe may appear calm when viewed from a distance, but beneath that quiet surface, extraordinary events unfold constantly. Across the vastness of space, stars explode, neutron stars collide, and magnetic fields twist with such intensity that they briefly outshine entire galaxies. These events release staggering amounts of energy, yet they remain almost completely unnoticed on the scale of the universe as a whole. The reason is simple: distance. When violent cosmic events occur millions or billions of light years away from one another, their immense energies disperse into the surrounding void long before they can interact with anything else. The result is a universe that looks serene from afar, even while astonishing phenomena erupt within it. One of the most dramatic events in astrophysics is the death of a massive star in a supernova explosion. Stars spend most of their lives quietly fusing hydrogen into helium deep within their cores. This process generates energy that pushes outward against the inward pull of gravity. For millions or billions of years, that balance keeps the star stable. But eventually, the balance fails. When a massive star exhausts the nuclear fuel in its core, gravity takes over. The star's inner layers collapse inward with incredible speed, compressing matter to densities so extreme that atomic nuclei are forced tightly together. The collapse halts abruptly when the core becomes a neutron star, a compact object so dense that a teaspoon of its material would weigh billions of tons on Earth. That sudden halt produces a violent rebound. The outer layers of the star are blasted outward in an explosion known as a core collapse supernova. For a brief period, the exploding star can shine as brightly as an entire galaxy. Yet despite the energy released, these events are separated by immense cosmic distances. The nearest supernova visible to the naked eye in recent centuries occurred in the year 1987, when a star exploded in the Large Magellanic Cloud, a small neighbouring galaxy. Even that relatively nearby event took about 160,000 years for its light to reach Earth. The universe operates on timescales and distances so large that even the most spectacular explosions unfold quietly across the cosmic landscape. Some events are even more energetic. Among the most powerful phenomena ever observed are gamma-ray bursts. brief flashes of extremely high-energy radiation that can release more energy in a few seconds than the Sun will produce in its entire lifetime. For decades, these mysterious bursts puzzled astronomers. They were first detected in the 1960s by satellites designed to monitor nuclear explosions on Earth. Instead of human activity, the detectors recorded bursts of gamma radiation arriving from distant parts of the sky. Understanding these events required decades of observation and theoretical work.